Hello, everyone, and welcome to Soil Sensors and Cadavers and Other Ideas to Expand the Uniqueness of Your Research. Today's presentation is scheduled for 20 minutes, followed by 10 minutes of Q&A with our presenters, Leo Rivera, Doug Cobos, and Chris Chambers, whom I'll introduce in just a moment. But before we start, a couple of housekeeping items. First, we want this to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, no worries. We're recording the webinar and we'll send around a link to that recording via email within the next 3 to 5 business days. Okay, let's get started. Today we'll hear from Leo Rivera, Doug Cobos, and Chris Chambers, who will discuss inventive ways people have used our instrumentation, what to consider before using a sensor in a novel way, and research trends we're seeing in recent fellowship applications. Leo Rivera operates as a research scientist and hydrology product manager at Meter Group, where he's the force behind application development in meters hydrology instrumentation, including the HyProp and W4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. Doug Cobos is a research scientist and the director of research and development at Meter. He also holds an adjunct appointment in the Department of Crop and Soil Sciences at Washington State University. His current research is centered on instrumentation development for soil and plant sciences. And Chris Chambers operates as the environment support manager and the soil moisture sensor product manager at Meter Group. He specializes in ecology and plant physiology and has over 10 years of experience helping researchers measure the soil plant atmosphere continuum. And so without further ado, I'll hand it over to our panelists to get us started.
Thanks, Brad. And thank you everybody for joining today. I think this is a presentation that Chambers, Doug, and myself are both really excited to give. One of the best things about what we do at Meter is getting to see all of the ways that people use our instrumentation to solve really unique problems. And so, when we thought about this, I thought we just thought it'd be fun to share some of those unique applications that we've seen over time. So Brad, go ahead and go to the next slide. So we have 3 goals coming out of this presentation. The first goal is to go over the most inventive ways people have used our instrumentation in their research, and we've seen a lot. And so it's fun to show some of these pieces, but there's so much more that people do beyond what you're going to see today. We're also going to talk about what to consider before using a sensor in a novel way. There's a lot of things that you can do wrong, and we want to make sure that you at least have some ideas of what to think about before you try these unique applications. And we're also going to go over research trends we've seen and our predictions about future trends based on years of reviewing fellowship applications from our G.A. Harris Fellowship, which Chris Chambers will talk about near the end of our presentation. Go to the next slide, Brad. So just to give you a little bit of background on where a lot of this is coming from, we've had 20+ years of working with researchers, talking with them about their applications, what things they need to consider, and how to try and make measurements in the right way, or how to resolve things when things went wrong. And so we've just learned a lot over that time, and we've seen a lot of really interesting applications. We've also seen a lot of trends in research from the 10 years that we've ran our G.A. Harris grant. We've reviewed hundreds of grant applications, and every year you kind of see shifting trends in where research is growing. So it's going to be fun to share what we've seen over that time and where we see things going. So let's go ahead and jump into it. Brad, go ahead and go to the next slide. And we're going to talk about the inventive applications first that we've seen with our instrumentation and research. So let's go ahead and jump into the first case study. So in this first case study, we're going to talk about stem water content and tree water use. In this project, PhD candidate Ashley Matheny of the University of Michigan used soil moisture sensors to measure volumetric water content in the stems of 2 species of hardwood trees in a northern Michigan forest, mature red oak and red maple. Though both types of trees are classified as deciduous, they have different strategies for how they use water. Oak is anisohydric, meaning the species doesn't control their stomata to reduce transpiration, even in drought conditions. The isohydric maples are more conservative. If the soil starts to dry out, maple trees will maintain their leaf water potential by closing their stomata to conserve water. Historically, tree water storage has been measured using dendrometers, and sap flow data, but Ashley's team wanted to explore the feasibility of inserting a sensor that's normally used in measuring soil moisture, a capacitance type soil moisture sensor, and embedding that in tree stems as a real-time measurement. But ultimately, the goal of this unique application of soil moisture sensors is to understand the different way these two types of trees use stem water in various soil moisture scenarios. Go ahead and go to the next slide, Brad. So Ashley used meteorological, sap flux, and stem water content measurements to test the effectiveness of soil moisture sensors for measuring tree water storage and water use dynamics. They also calibrated the sensor, the output of the sensor, to the wood density. And you can see the results of some of those measurements in the graph on the right here. And what they found is that the volumetric water content measurements in the stems described tree water storage dynamics, which correlated well with the average sap flux dynamics. They also observed exactly what they assumed would be anisohydric and isohydric characteristics in both trees. When soil water decreased, they saw that the red oak used up everything that was stored in the stem, even though there wasn't much available soil moisture. Whereas in the maple, the water in the stem was more closely tied to the amount of soil water. After precipitation, maple trees used the water stored in their stems and replaced it with more soil water. But when soil moisture declined, they held on to the water and used it at a slower rate. And this is just really interesting to see how they could take something like a soil moisture sensor and use it to measure tree water use dynamics.
Using a capacitance sensor to measure stem capacitance. I love it.
So a couple of comments from me here too. Nice one, Chambers. I haven't seen in the literature yet. Of course, I haven't read up on this a lot real recently, but it seems like this is, it ought to correlate pretty well to dendrometer data. So, whoever wants to do the comprehensive study that looks at the stem capacitance versus dendrometer data would be, well served to do that. Also, that graph on the lower left, looking at the actual sap flux along with the storage parameter or the capacitance parameter, Chambers, that is proving to be pretty powerful in plant water dynamics. So super cool research there. And one last thing, Brad, will you go back to the last slide, please? If you do this work, please insert your sensor all the way into the trunk. The illustration there may be a little bit misleading.
Thanks, Doug. All right, let's go ahead and move on to our second case study now. I'll be honest, this is a topic I never thought I'd talk about, soil moisture and landmine detection, but it was really an interesting one to read up on. So, anti-personnel landmines are one of the most dangerous environmental hazards worldwide. Each year, thousands of people are injured by landmines buried in 80 different countries. On top of this, they're difficult to detect. So, Ben Wallen, a PhD candidate and active military officer at the Colorado School of Mines, is using soil moisture and temperature sensors to model, simulate, and predict how environmental conditions affect landmine detection performance. They installed an array of soil moisture and temperature sensors in a field site in order to understand how landmines buried at different depths affect spatial patterns of soil moisture. And by gaining a greater understanding of these dynamic environmental conditions, Wallen thought he could better calibrate the numerical models used in detection technologies, such as ground penetrating radar. In addition to soil moisture and temperature sensors, he used an IR camera to detect surface temperature differences prior to a saturation event, during the saturation event, and then afterward. Go ahead and go to the next slide, Brad. In this study, Wallen was able to see differences within the with mine and without mine treatments. The soil moisture in the disturbed soil 2.5 centimeters below the surface with no landmine inserted matched very well with a shallow buried landmine. But then deviation occurred when there was a saturation event, which one might expect with an impedance like landmine. And there was a break from this relationship. For a deeply buried mine, both the soil moisture and temperature in the disturbed soil 2.5 centimeters below the surface had a strong correlation with the response to the dug disturbed hole. And ultimately, the goal of this study, according to Wallen, is to provide pertinent information that will improve landmine detection technologies, understanding how temperature contrast impacts remote sensing technologies, and understanding how the soil moisture signal impacts things like ground penetrating radar. And so it's just really interesting in the study to take what is, soil physics and apply that to something like trying to detect landmines. And so this was one that was just interesting to read up on.
So an interesting tidbit on this one, there was an earlier study also using our soil moisture sensors for, to aid with landmine detection. And instead of framing it to measure water content and look at those effects on the GPR, they were actually using the dielectric permittivity measurement from the sensors, which is a little bit odd. Most people that install a soil moisture sensor don't care about dielectric permittivity. They care about the water content in the soil. But because it's actually the dielectric permittivity that attenuates the GPR signal, it was more interesting for them to use the primary measurement out of the sensor as opposed to the derived measurement of water content that most people care about. Just an interesting anecdote, I think.
Oh, that's good. Thanks, Doug. Yeah, it's just really interesting to take soil physics and apply it to something like this.
So one other little tidbit here. There was almost 100% chance that the Colorado School of Mines was going to get funded for this particular research study.
Thanks, Doug, for that awful pun. All right, on that note, let's go ahead and move on to our third case study. All right, so this case study is going to turn a little bit darker. And as you guys may have imagined, if you read the title, that we were going to go to something like this. But this case study focuses on soil moisture and forensic science. Again, something that I never really thought I would be reading about or talking about, but is really quite fascinating. So Stacy Taylor, her advisor, Dr. Jennifer DeBrin, and their research team at the University of Tennessee, along with other forensic scientists, are looking at better, more accurate ways of determining the post-mortem interval or time of death. So when a human body decomposes, microbes and nematodes become abundant in the soil surrounding the body. The types and maturity of these organisms may be a means of determining the time of death, but thus far, most studies have focused on short post-mortem timeframes. So Taylor, working in conjunction with the UT Anthropology Research Facility, where they have a cadaver farm, is measuring biological and chemical changes in soil composition brought about by long-term human decomposition. Some of the changes in soil composition that occur during both vertebrate and invertebrate decomposition, basically anytime you have a decomposition event that is not composed of plant litter, it creates what's called a hotspot of nutrient enrichment. Unlike plant litter, which decomposes very slowly, with a vertebrate system, you have a tremendous amount of protein and fat, which changes these properties. So to try and characterize this process, volumetric water content, electrical conductivity, and temperature sensors were installed in the soil surface so they could measure the impact the decomposition produced immediately on the upper layer of soil. They also used an RT1 air temperature sensor to track accumulated degree days, which are based on ambient air temperature and correlate with maggot growth and development rates. So again, we're taking these measurements that are typically used for soil and plant sciences and then applying them to a different field of study like forensic science. Let's go and move to the next slide, Brad. So Stacy was surprised at how informative and eye-opening the results were. These hotspots change the ionic strength of the soil water, and that is highly correlated to the electrical conductivity measured by the soil moisture sensors, as one might expect. The soil changes, in particular the EC and temperature, are not just general deviations though, but show clear stages as decomposition progresses through time, indicating they might be useful as time markers. When tracking a succession of events, these events happen at particular time points and are associated with certain decomposition stages, i.e. bloat, active decay, advanced decay, or skeletonized remains. Sorry, again, I know these are not the funnest things to talk about, but it's just a really interesting application.
Oh, come on, Leo, don't be so squeamish.
Thanks, Chambers.
I feel like I'm on an episode of NCIS here.
Well, I think NCIS has led to a lot of these studies, thanks to shows like that in NCSI. But so, for example, you might see traces of increased electrical conductivity followed by a drop if that drop happens at the same stage of decomposition over and over, then that you know that you have a time marker. And when you gradually accumulate some of these time markers, that can potentially inform some of the existing estimates of how long something has been there. The implications of this study will help nail down many of the intrinsic controls on the decomposition process. And once they understand that, they'll have a better idea of how to employ these estimates of postmortem interval, which will hopefully bring better justice and more peace to the families of crime victims. So again, a really dark but interesting application of soil science. So let's go ahead and jump to our next case study number 4. And I'm actually going to let Doug talk about this one because this one's a little bit closer to home for us.
Yeah, so let me tell a little story here. So this was back in 2002, 2003. Some scientists from NASA's Jet Propulsion Lab stopped by our booth at AGU and said, hey, you guys measure water content, liquid water content, and you measure thermal properties of soil? We need to make those measurements on Mars. And so that started a cascade of events that led us to develop the thermal and electrical conductivity probe, which you'll see in the bottom middle, that actually flew to Mars in 2007 aboard the Phoenix Mars lander, which is up there in the top right. And so this was basically a full-on repackaging of existing technology, existing sensor technology that is used all the time here on Earth, but repackaging and repurposing it for a Mars mission. And so it was an interesting mission and an interesting process to do the customization of the sensor tech, but it is really just an extension of what we're talking about here today, where using existing sensor and instrumentation technology for novel purposes. And I guess probing the soil on Mars probably fits the bill of a novel purpose. But anyway, if you look at the picture on the bottom right, that is actually a picture from the surface of Mars with the thermal and electrical conductivity probe bolted on by the robot arm scoop. And this mission flew and landed in the northern polar region, where it did discover ice. They knew the ice was there from remote sensing, but this validated that there was a shallow icy layer. But even when uncovering that shallow ice and exposing it to solar radiation, there was still no evidence of liquid water. But measurements, all the terrestrial measurements, the water content, electrical conductivity, the soil thermal properties, the relative humidity measurements, they all worked really well. So it's a super fun project, and was happy to be part of it.
Doug, didn't they take wind speed measurements by sticking the thermal probe up in the air too?
They did, yeah. So all those little spikes there had the ability to be heated. So they did do basically hot wire anemometer measurements of wind speed as well. Yep. Then go ahead, Leo. Leo may be muted.
Yep. Yeah. So we'll go ahead and jump over to our next case study now. So in this last case study, we're going to actually talk about avalanches and thermal properties of snow. So I'm going to start this out with a little Wired magazine story. So in February 2011, Wired magazine wrote a story on a team of researchers. They didn't refer to them as a team of civil engineers studying granular mechanics. Instead, they named them one of 7 teams of mad scientists and called them snow bombers. And Rich Scherzer and his team at Montana State University fall into this group. It's long been empirically understood that avalanches tend to form above weak layers of snow. And Rich, while he was a PhD student at Montana State, and his colleagues were studying how the orientation of snow crystals correlates with weak layers. Most models of granular mechanics assume that the material's microstructure is randomly arranged. However, snow layers seem to show irregular arrangement. Qualitatively, people have known for a while that when you look at certain snow layers, chains of these ice grains seem to be forming. So their goal was to mathematically model how that might affect the material properties of snow, including thermal properties. Let's go and move to the next slide, Brad. So in order to study the thermal properties of snow samples, the researchers' team wanted a way to measure thermal conductivity in 3 directions. As you can imagine, this was a challenging task for the existing technology at the time. Snow has a very low thermal conductivity, so if you add a lot of thermal energy to snow, since it's very insulative, you'll tend to raise the temperature. And that's obviously not something you want to do when you're trying to measure properties of snow. So this causes 2 issues. One, it melts the snow in the neighborhood of the probe. It also artificially induces the same thermal processes that cause the crystals to change size, shape, and orientation. So 2 things you don't want to do when you're trying to make this measurement. Luckily, at the same time, Meter's research scientists at the time, Decagon, were focused on reducing the contact resistance errors that occurred when using the large TR1 needle to measure thermal conductivity in large grain samples. So this actually made the TR1 needle a good candidate for measuring thermal conductivity in snow. So Rich reached out to Decagon at the time, our Meter research scientist, and worked with us, and we were able to modify a version of, at the time, KD2 Pro, but now the device would be called the Tempos firmware, to be produced with the low power version that would work in snow. Their measurements showed anisotropy, or changes in thermal properties due to the orientation of the snow chains. The orientation of the chains follows a direction of increased conductivity, and the directions that are perpendicular to the chains tend to decrease in conductivity. So using needles to measure in 3 different directions simultaneously has given them the ability to measure these properties. And they expect that this orientation also affects other properties like strength and stiffness. And this is what they've continued on to study and show throughout their research. And so it's just a really interesting application of thermal properties measurements in snow. It's a little bit different than what we've been talking about. So I think we'll go ahead and move on now that we've talked about some of our case studies. Let's go ahead and jump over to our next section, which is what to consider. And we'll let Doug Cobos take over here.
All right, so the first thing that I would ask you to consider before using some of our instrumentation for a novel purpose is to consider breaking off a phone call, okay, or an email. Give us a ring. Brad, go ahead and go to the next slide. So please don't be afraid to reach out and ask us. So if you guys are familiar at all with Meter environment, nearly all of us come from a field research background, right? Or at least a lab research background. And so we are scientists at heart, and we've been exactly in your shoes. We love to consult on unique research, and we very much want you to be successful because we know what it's like when experiments don't work right because of instrumentation issues. And we're also instrumentationalists. You know, our job is here at Meter trying to help develop and support instrumentation that enables you guys to do some groundbreaking research. But we know more about our instruments than anybody else. We hope so anyway. And so we know about the limitations, and we know about what they can and cannot do. So getting in touch with us would be a really, really good idea if you're dreaming up some novel ways to use the instrumentation. Brad, next slide, please. So a few things to keep in mind. We generally write conservative specs for our instrumentation, meaning that generally the instrument can go a little bit beyond what we write. We just try and be conservative to make sure that people don't run into problems. And so, you know, we had a case a while back. Actually, we've had several people reach out about trying to measure moisture in compost, and active compost systems get really hot, and the temperature of those systems exceeds the spec that we write on our sensors. But that's a pretty conservative spec, and so when people have reached out, we said, yeah, go ahead and go for it. It's probably going to be fine, and it has been fine. And there's been, you know, really good research done in that regard, even though the application didn't strictly fit into the specifications. Sometimes using an instrument in a novel way can invalidate the calibration or change the data. But if you reach out and we can help you understand how it changes the data, then often that data can either be recalibrated or corrected, okay, to where it's meaningful again. So one example of that was a research group that wanted to measure surface wetness of buildings, and they wanted to see if they could use our leaf wetness sensor or Phytos 31 for that application. And the answer would be, well, with the way it's configured, strictly no, because sticking that instrument on the building would change the baseline output. But if you adjust your expectations for the baseline output, then you're good to go. And so this was, some good research that was done on actually corrosion and wetness duration of a metal building. Also, we've had customers that wanted to use our Taro sensors or our water content sensors in extremely salty soil, like ridiculously high EC soil. Think saltier than seawater. And this would affect the output of the sensors, but the sensors still give repeatable output. It just wouldn't be usable with the standard calibration. So with a custom calibration for their water content sensor output, they got great data out of this study. So that's a couple of examples on where if you just reach out, we can help you come with some strategies to get some really good data. Sometimes you may even need to modify the instrument. So many of you are familiar with the leaf barometer, the SC1, used to measure still model conductance. Well, it can measure conductance of many things. And there was one research group that wanted to measure the effects of basically laser etching apples. So instead of putting the little sticker on them, laser etching in the type and the date and things like that, and wanted to see how much that would compromise the cuticle and allow water to migrate from the inside the apple to the outside. And so all they had to do was make a couple of modifications to the leaf barometer, and it worked great for that study. Also had people that wanted to measure water potential in soil and other materials at high temperatures, higher than our WP4C can control the temperature. But if you use external temperature control and twiddle a little setting in firmware that we can tell you about, then you can turn the internal temperature control off and use external temperature control and get up to those high temperatures. And so with just a little bit of modification, I guess the story that Leo told about the firmware modification on the KD2 Pro or Tempos to reduce the amount of heat it input into the snow so the snow didn't melt. I mean, these are things that can be done and can enable some unique research. But with all that said, sometimes we're going to have to tell you, well, it simply can't do that, or at least caution you and say, this has a very high chance of failure. So, we've had, as Leo mentioned in the first case study, we've had people put sensors into trees to measure the stem capacitance or the water status in the tree trunk. Well, you have to be a little bit careful pounding those in. You don't want to use a metal hammer and try and whack those in. You're going to need to be careful with the pilot holes and things like that. Also, we've had people ask, hey, we need to measure the water content of basically this conductive material, like think about metal shavings and stuff like that, and that's not going to work with the electromagnetic techniques. And so there are plenty of cases where we have to just say, yeah, that's probably not going to work. You're welcome to try, but this is probably what's going to happen. So basically, this is just a long way of saying, if you want to use a piece of instrumentation from any company, from any manufacturer in a novel way, please just go ahead and get in touch with the folks there, because they're going to be able to help you out, either help you have success or save you a whole lot of work and potential heartbreak and sadness if it doesn't work out. So there you see on the slide, here's a good way to get a hold of us: email or call. So please do it.
Thanks, Doug. The moral of the story is always give us a call. We're willing to talk about this.
And be careful banging on electronics. That leads to heartbreak in many cases.
Yeah, that's a good one to think about. All right. Well, I think on that note, let's actually hop over to research trends now, and we'll let Chambers take that.
Okay. So Meter does a annual research fellowship grant for grad students, and it's called the Grant A. Harris Fellowship Award. Grant Harris was an influential person at Meter who helped guide it through its early stages of development. And it's a way for us to stay active in our scientific community. We're instrumentalists, but we're all researchers at heart. So sometimes we have to live vicariously through other people's research. But it's also a way for us to invest in future scientists and help out some grad students that just need a few more instruments to make their projects awesome. And we have a few criteria on which we evaluate these on the next slide. And some of the things we look at are novelty, impact, and chance of success. And novelty is something we score highly, as well as impact, like how much does it have the ability to move the field forward. And so those two things kind of are really weight a proposal towards success. But we also want there to be a high chance of success in the project, but sometimes that is just decreased if you're doing something new or you can't evaluate that very well. So we'll look at the next slide and look at some of the topics that we've come in. Now, we've been doing this for about 10 years. I've only got 3 years worth of information in here, and I just kind of put things into broad topics and just to see what pops out for research trends. And some recurring things that you'll see, back in 2018, there was a lot of urban ecology, climate change, and ecophys research were important. But hydrology and ecophys kind of emerged through several of them. But then the smaller ones are some of the really interesting ones that can sometimes be the really unique and novel ones. And like biochar amendments first started showing up about 10 years ago, and then they were one of the main ones for a few years, and now we're starting to see those kind of fade into the background a little bit more. Next slide, please. Again, ecophys and hydrology are big ones, and just because that a lot of proposals fall into that topic doesn't mean that there's not novel approaches within there. Things like machine learning start to pop out more if I were to take another layer of topics here. And we make instruments that lend themselves to ecophysiology and hydrology. So it makes sense that we'll get more proposals on those types of things. And then we get cool things that you wouldn't normally think our things would be good for, like measuring habitat for avian diet and aquatic community ecology. Okay, next one, Brad. And then in 2020, soil health is starting to emerge more as a topic. So we're seeing urban soil health and urban ecology just seem to be kind of growing in their frequency in our applicant pool. But then again, we still have ecophys and hydrology carrying through. And I think we'll end, I think just Leo, Doug, what do you guys think will be emerging as new trends? Or what topics do you think we'll be seeing in the coming years?
Yeah, I think one thing that's been interesting to me is how dominant and predominant ecophys has been, and also the growth we see in urban ecology. But I anticipate that we'll also see continued growth in the soil health area, along with regenerative agriculture. I anticipate those are two topics that we'll see continue to grow. Yeah,
climate change has been popular and important for a long time, but it's not declining in importance at all. And Leo, you're right. I think soil health has a lot of buzz right now. I think that's kind of catching on as something that's important for us to pay attention as a society.
Yeah. So bring on your applications for this next year, guys. We're excited to see what y'all are trying to do.
Application period is open for any graduate students that need a bit of gear for the next. It ends in middle of January.
Awesome.
Well, I think we're just about out of time there. Let's see.
Yeah, we'll let Brad jump in.
Yeah, I think we are a little over time, but we do have time for a few questions here. We'll take a couple minutes to take some questions. And thanks again to everybody who's joined us today. Again, if you have a question, type it into the questions pane. Our panelists will see that. We'll try to get to as many as we can. If we do not get to your question, we do have them recorded along with the email that you registered with. And so one of our panelists will be able to get back to you if they don't answer it live here during this webinar. Maybe first off, Chambers, could you, for those interested in the audience, could you maybe just give some quick information about where they could go to learn more about the Grant Harris Fellowship up and where they could apply and the requirements for that?
Yeah, and if you go to metergroup.com and search for Grant Harris, I can't remember the exact URL, then you'll go to an application page and there's information about your proposal, the format, all the I's and T's that need to be dotted, and an actual, you can submit your application right online, and with the proposal, the instruments that you want, and the usual stuff, the CV and letter of support from your advisor. We'll check it out and we review the applications in February and try to get the instruments to you by March. So we try to just have a quick turnaround time, right? So you're not waiting months and months to find out whether or not you got your grant proposal approved.
Okay. And that's for graduate students in the US and Canada, is that correct, Chambers?
That's correct. Mm-hmm.
All right. Let's see here. I do have one here. Early on, you guys talked about, I think this was Doug who was mentioning, contacting us to ask and see what we can do to help out with your project. Have you guys ever had somebody propose their project and basically you say, no, there's no way we can help you, but then they go along with it and it actually does work out in spite of your negativity?
Chambers,
I'll let you take this one. No. We give the best advice that we can possibly give. With our experience with the instruments, with our knowledge of, but we're not omniscient, and sometimes we learn new things from our clients just about every single day, and we try not to be negative, but just give the best advice that we possibly can.
Yeah, I mean, it really, with all of these things, it's kind of a continuum, where it's maybe a normal distribution of chances of success, right? And at some point you're down on the tail end where your chances of success are so small that we try and caution strongly that it's probably not going to work. But sometimes you get lucky.
And yeah, burying data loggers is a good one, because we've seen just some terrible situations where people buried their loggers, and for a long time we're just like, don't even do it, don't even try it. And then a persistent team was like, well, what about this and what about this? And we gave them told them what the consequences are and what they would need to do to protect it, and they actually put together a really nice buried logger project, and so that was a complete success story.
Yeah. Yep.
All right. I think maybe we'll have time for one more. We can sneak one more in here. So when this one might be kind of specific, but in getting back to that question about with decomposition in the soil and those kinds of things. They're asking what kind of calibration would you even use to get those measurements out of the soil?
Ooh, I can touch on that one a little bit. So, this one is a little bit different because the sensor was in the soil, and so it's in an environment that it's technically designed for. I think where things will begin to shift is when you start to see higher trends in the electrical conductivity, which might cause that to deviate a little bit. And I think there are ways you could get around that by developing, calibrations based on EC. But I don't know if there's everything that we can account for. But one approach they did take that I didn't talk about is they did take soil cores as well. So they measured other soil properties to go with that to help better understand what was going on along with the soil moisture measurement.
Yeah, so you guys may or may not be aware that we do custom calibrations for our soil moisture sensors here at Meter, where you can send us a sample of your particular soil and we'll construct a custom calibration to convert from the sensor output to an accurate water content number. But please, please do not send us decomposing flesh for a calibration. We absolutely will not do that one.
I think
Yeah,
they're
you have to draw the line somewhere.
Okay, well, thanks you guys. That's going to wrap it up for us today. Thanks again for everybody for joining us. We hope you enjoyed this discussion as much as we did. Thanks for your great questions. Again, if we did not get to your question, one of our panelists will be able to get back to you individually and answer your question. Please also consider answering the short survey that will appear after this webinar is finished to tell us what other types of webinars you'd like to see in the future. And again, for more information on what you've seen today, visit us at metergroup.com or contact us at that phone number and email that you see there on the screen. And finally, look for the recording of today's presentation in your email or a link to that recording. And stay tuned for future Meter webinars. Stay safe and have a great day.